Hello everyone, welcome back to Algebra. Today we're going to talk about the correspondence theorem. This is another theorem that is usually treated with the isomorphism theorems. So let me state what it says. The theorem gives you a correspondence so that you can compute subgroups of a quotient group. So it says the following: let n be a normal subgroup of group G. Then there is a correspondence between, so the subgroups H of G that contain N and the subgroups of the quotient G modulo N. And the correspondence takes H to H modulo N. Okay. And moreover, if this correspondence is, let's call it psi, psi takes normal subgroups to normal subgroups. So namely, if n is contained in H and H is normal in G, then H modulo n is actually normal in G modulo n. This fact that this part that if H is normal in G, N is normal in G, that the H modulo N is normal in G modulo N, that was actually used in the third isomorphism theorem. So let's prove this correspondence. So we want to prove that there is a bijection like this that preserves normality. Let's do the proof. So first of all, let's check that the correspondence is well defined. So by well defined here, I mean that if H is a subgroup that contains N, that then this is a subgroup of G modulo N. So let H be a subgroup of G with N contained in H. Then the fact that N is normal in G implies that N is in particular normal in H. And therefore, H modulo N is a quotient group. So it is a group and it is a quotient. And clearly, H modulo N is contained in G modulo N. Within they are contained and it has the same operation, so it is a subgroup. These are cosets of the form Hn, as H ranges over all H, which is contained in the set of cosets which are Gn, as G ranges over all of G. And then you can set up a group structure for H modulo N. So the group structure just among these cosets, that is a group, and it is a subgroup of the group structure that these cosets have on their own. Okay, so that is well defined. So now let's prove that the correspondence is onto. So what do we need? We need to have, suppose I have a subgroup of the quotient group, a subgroup. We want to show that there is some subgroup H in G with N containing H such that H modulo N is precisely this subgroup G, this subgroup S. Okay, so what is this subgroup? This subgroup is going to be some collection of classes of cosets, G1n, G2n, up to some GSn. Okay, and what I'm going to define as my H is going to be those G's in G such that Gn is in S. And well, the question is whether this is a subgroup or not. So let's prove that H is indeed a subgroup, and it's going to have the properties that we want. Okay, so we have a subgroup of G modulo n, as is given by G1n up to Gsn. By the way, we can assume that that is the identity element. It has to be a subgroup, so there is an identity element. The identity element in the quotient group is just n. And we've defined H to be those elements in G such that Gn is in S. And I want to show that that is a subgroup. So we have a criterion for subgroup. Now if H1 and H2 are in H, then I want to show you that the product of those two will be in H, and that it is closed under inverses. So first of all, if H1 is in H, then H1 inverse is also in H, because well, if H1 is in H, that means by definition that H1n is in S, and S is a subgroup. That means that H1n inverse is in S because it is a subgroup. And this is, in fact, H1 inverse n, and that tells me that H1 inverse is also in H by the definition of H. So H is closed under inverses, and it is closed under multiplication, because if H1 and H2 are in H, then that means that H1n and H2n are in S, and therefore, since again S is a subgroup, we have that H1n times H2n will be in S, but this is H1, H2n, by the way, cosets multiply, and if this is in S, that means that H1, H2 is in H. So therefore, this tells me that H is a subgroup of G. And on the other hand, what is the map? What happens if I use the correspondence? So H, those G's in G such that G and are in S. What happens if I send it to H modulo n? By the way, notice that n is contained in H, because if n is in n, then n is n, which is an element of S. So it is a subgroup of H. And H modulo n, well, there will be, by definition, will be H n with H in H. But that is, by definition, are those HNs such that, well, if H is in H, if H n is in S, which is S. And therefore, the map, the correspondence is surjective. Great. So now let's prove that the correspondence is injective. So suppose I have two different subgroups, or two subgroups of G, both contain a n. Whoops. Both contain n, and suppose that their quotients H1 modulo n is actually the same as H2 modulo n. Then that means that if H1 is in H1, then H1n, which is one of the cosets that are in here, would be also in H2 modulo n, and therefore H1n is actually one coset with a representative in H2, so it is H2n for some H2 in H2, but then that tells me precisely that H1n, that H1, which was arbitrary, is in sorry about that. H1 is in H1n, which is H2n, which is contained in H2. So this tells me since H1 was arbitrary, little h1, that all of capital H1 is contained in H2, and similarly, we can conclude that H2 is contained in H1 by symmetry. And therefore, we get what we want, which is that H1 equals H2, and therefore it is injective, and the correspondence is in fact bijective. So we have a bijection of these two sets, as in the proof, as in the statement. We have a bijection between subgroups that contain n and the subgroups of the quotient. Last, I said that this correspondence takes normal groups to normal groups, or normal subgroups to normal subgroups. So let first H be normal in G, such that n is contained in H. Then we actually have a homomorphism that goes from G modulo n to G modulo H. That sends G modulo or Gn to Gh is a homomorphism. I'm going to leave that as an exercise. This is an interesting exercise, so you know these exercise tests that you understand what quotients and homomorphisms are. So check that this is a as it is a hom. And so this is homomorphism. And what is the kernel? The kernel will be precisely the cosets that go to the trivial coset. So when G is in H, so that is precisely H. So the kernel is actually H modulo n. And therefore, since H modulo n is a kernel, that is normal in G modulo n. So if H is normal in G, H modulo n is normal in G modulo n. On the opposite direction, if we have a subgroup that is normal in G mod n, so we have a subgroup H a priori, H is just a subgroup, such that the quotient by n is normal in G modulo n, then there is another hom that goes from G to G modulo n, that is a homomorphism, that's just reduction modulo n, and then this goes to G modulo n modulo H modulo n, that is another homomorphism. H modulo n is normal in G modulo n, so I can do this quotient, and this is a hom. The composition of these two different quotients by normal subgroups is a hom, is a homomorphism, and it has kernel. What is the kernel? All the way here, from here to here, the kernel is n, but then from here to here, the kernel in here is H modulo n, so the kernel from here is H. So since KH is a kernel, that implies that H is normal in G. And that is exactly what we wanted to prove, that the correspondence sense, if it's normal in G, is normal in the quotient, and if it's normal in the quotient, was normal in G to begin with. So let me do an example of how to use this correspondence theorem to classify all the subgroups in a quotient. Let's use the correspondence theorem to do the following. We're going to describe all subgroups of z modulo 12z. Now, that is easy to do because this is just this is a group with 12 elements, 0, 1 up to 11 modulo 12. So we can just computationally find them all quickly. In fact, Z modulo 12 is cyclic, so all the subgroups will be cyclic groups, so generated by one element. So you can just check all the generators and see what do they generate and find all the subgroups. But let's entertain me and let's use the correspondence theorem for this. What is happening here is that this is actually a quotient. There is a subgroup of the integers, and then we're doing a quotient. That is a normal subgroup. Every subgroup of an abelian group is normal. So what the correspondence theorem tells me is that the subgroups of Z modulo 12Z are actually in correspondence with subgroups of the integers that contain 12Z. And the correspondence tells me that actually if I find one of those h's, then the correspondence will just be that h modulo 12 will be one of those subgroups, and every subgroup comes in this way. So let's find these subgroups instead. But we know that the subgroups of Z are cyclic. So they are all of the form nz for some integer n, which we can pick to be positive. So for some n bigger or equal to 0. Okay, so those are all the subgroups. And now what we actually want is also, these are the subgroups of the integers, but I want subgroups of that form that contain 12. And if they contain 12, that means that that n has to be a divisor of 12. Because these are the multiples of 12, so 0, 12, 24, and then also minus 12, minus 24, etc. These are multiples of n, so 0, n, 2n, etc., and then minus n, minus 2n, etc. And these multiples of 12, the multiples of 12 will be within the multiples of n if and only if n is a divisor of 12. But I can find all the divisors of 12, all the positive divisors of 12. Those are precisely, well, there is n is, it can be 1 or 2 or 3 or 4 or 6 or 12. Okay, so what are those subgroups then? There is, for n equals 1, I have z, all of z, or I have 2z and 3z and 4z and 6z and 12z. Through the correspondence, this corresponds to the subgroup z modulo 12, which is the entire group z modulo 12. This corresponds to the multiples of 2. This corresponds to the multiples of 3. This one corresponds to the multiples of 4. This one corresponds to the multiples of 6. And this corresponds to the multiples of 12. So what subgroups are those? This is everything up to 11 modulo 12. This one is the multiples of 2. So 0, 2, 4, 6, 8, 10, and then 12. So that is it. This is the multiples of 3. So 0, 3, 6, 9, and then it would be 12. So that is it. These are the multiples of 4, 0, 4, 8, and then 12. These are the multiples of 6, so 0 and 6. And these are the multiples of 12. 12 is 0, so this is just the trivial subgroup. So these are all the subgroups. These are precisely all the subgroups of Z modulo 12Z, and we found them using the correspondence theorem. So in this way, you can always find all the subgroups of a quotient if you know enough about the subgroups of the original group. Okay, so next time we are going to be talking about finite abelian groups and their structure.